Hello, I'm David Shin, and this is Lab 6, Magnetic Molasses. So, the purpose of this lab is to observe a falling magnet through aluminum foil, and we measure the time of the magnet falling for 5 different trials, and we generate a computational model in GlowScript. The key physics principles used in this lab are Faraday's law and various magnetic field equations, and in the end we found that our simulation was very accurate. So basically, to sum it up, we have a long metal tube that's wrapped in aluminum foil, and we have a small magnet, and we just drop it through the aluminum tube, and we can see that the induced magnetic field slows down the magnet as it drops to the aluminum foil, and we measure the time it takes for the aluminum foil or the magnet to reach the top of the tube to the bottom of the tube. So you can see here, again, reinforcing those fundamental principles. This is Biot-Savart law, change in magnetic field is equal to this. Faraday's law, which is the change in flux, and Lenz's law that states that nature abhors a change in a magnetic flux. All do together because they all factor into each other, and by Lenz's law, Faraday's law will be negative, meaning that the induced field will be in the opposite direction as nature abhors this negative change in flux. And this deals with the change in magnetic field, which in turn causes flux. So here's our experiment. You can see that in this, the video shows one drop, but you can see that we drop a magnet from the very top, and then we time the time it takes to get to the bottom, and so we have 5 total trials that we timed, and we timed them and they all turned out to be about 1.3 seconds. You can see that they're all very close together as each trial doesn't really differ. They're pretty much the same trial, and so we just did it multiple attempts just to reinforce and have multiple data points just in case we had large sources of error for one drop. So here's our code. You can see that this picture is mostly for setting up. See that this is the beginning of the code here. You can see that this is setting different constants such as true or false, the length and the width of the magnet and the tube. And then you can see in this this is actually calculating the velocity of the magnet and the position of the magnet, and you can see that this is also calculating the net force, and it has vectors such as the magnetic force and force gravity. So this is the actual calculation of the forces done on the magnet. Then we just have here a common loop, the time loop, and then we have the, again from earlier, the magnetic force on the magnet, which is calculating here. You can see that the ring, we have an if statement, so saying that the current in the ring is greater than 0, so the induced current will do this to the ring. And you can see that all this code will eventually calculate out for the velocity of the magnet using the different forces that apply on the magnet in this case, which are mainly force gravity and the magnetic force. Here are the results. We find that at 0, velocity is pretty low, and then it kind of increases in like a negative logarithmic way, saying that it increases the most off the initial drop, and then as the magnetic force gets higher, as it opposes the change in flux, it slows down the magnet. You can see in this curve here. You can see here that this blue line is the upwards force due to the magnetic force, and then this red is the downwards force due to the force of gravity. So you can see that these two forces are opposing each other, which is why the velocity does not increase in a linear fashion as we'd expect if we were just to drop the magnet. So you can see here again, reinforcing that the velocity has a sharp increase at the very initial point, and then it levels off due to the magnetic force, and then again it becomes super steep when it exits the tube. So this is the portion where it's in the tube, and this is the portion when it exits the tube. This might be more accurate because the velocity is not constant within the tube, as you can see here, so this graphical model is more accurate. And so some large sources of error, we assume that flux remains constant and magnetic field changes linearly. This may not be the case due to the magnet misaligning itself or changing orientation. And so we assume a lot of constants, but in real life, there probably weren't as many constants as we assumed. And some large errors are inconsistencies in dropping the magnet. If we put it at an angle, it could change the amount of flux as the cross-sectional area changes. So if we dropped it in sideways, it might change the flux. And finally, inconsistencies in timing the drop. So what if the resistivity of aluminum was close to 0? So this decrease in resistance would lead to an increase in current due to Ohm's law, and we would see a higher induced current, which would slow down the magnet even more, as a higher induced current leads to a higher flux. And if there are holes in the tube, there would be less force magnetic, meaning there would be less induced current, which in turn would result in a weaker magnetic field, making our magnet fall faster. So they would have inverse effects. Thank you.